You're about to step into a reality so bizarre it makes the wildest science fiction look tame. Picture this: every second of your life, you're surrounded by unseen worlds brushing against our own, dimensions folded into space so tightly we can't even perceive them. Remember that spine-tingling moment in Interstellar when Cooper plunged through higher dimensions behind his daughter's bookshelf? What if I told you those mind-bending scenes might be closer to scientific truth than Hollywood fantasy? Right now, as you watch this, theoretical physics suggests our universe could have up to 11 hidden dimensions curled up smaller than atoms, shaping everything from gravity to the very fabric of time. For decades, scientists whispered about these extra dimensions as mathematical curiosities until breakthroughs in string theory turned whispers into thunderous possibilities. Today, we're tearing open the cosmic curtain to reveal 30 jaw-dropping facts about these hidden realms, from dark matter leaking through dimensional walls to black holes that might be gateways to higher realities. One of these facts could rewrite everything you thought you knew about existence. Number 12 will make you question whether time even flows the way we experience it. Whether you're a space enthusiast or just love a good cosmic mystery, this journey will stretch your mind across dimensions you never knew existed, ready to see beyond the limits of human perception. Let's begin. Let's peel back the first layer of this cosmic mystery. Imagine you're a character living in a world where everything is perfectly flat. No height, no depth, just length and width. This is the premise of Flatland, a brilliant thought experiment that helps us grasp how higher dimensions might work. In Flatland, beings can only move left, right, forward, or backward. If a 3D object like a sphere were to pass through their 2D world, they wouldn't see the whole sphere at once. Instead, they'd witness a dot that grows into a circle, then shrinks back to a dot, completely baffling from their limited perspective. Now, here's the mind-blowing part. We might be the Flatlanders. Our reality, as we perceive it, is built on 3 dimensions of space and one of time, Einstein's famous 4D spacetime. But what if that's just the tip of the cosmic iceberg? Enter string theory, the boldest idea in modern physics. While Einstein gave us gravity's dance across spacetime, string theory suggests there are 6 or 7 extra dimensions curled up so tiny, smaller than a trillionth of an atom, that we'd never notice them in daily life. Think of it like a garden hose. From far away, it looks like a simple 1D line, but up close, you see it's actually a 3D cylinder. Similarly, these hidden dimensions could be everywhere, folded into the fabric of reality at scales so small they're invisible to us. Why would nature need extra dimensions? Here's where it gets wild. In string theory, the fundamental particles of the universe aren't dots but vibrating strings. Just as a guitar string plays different notes depending on how it vibrates, these cosmic strings vibrate in higher dimensions to create all the particles and forces we know: electrons, quarks, even light. Without those extra dimensions, the math collapses. It's like trying to play a symphony with only half the instruments. The harmony just doesn't work. But wait, there's a twist. Not all theories agree on how many dimensions exist. Some versions of string theory demand 10 dimensions, 9 of space, 1 of time, while M theory, its more mysterious cousin, requires 11. Picture a cosmic origami. These dimensions could be compactified, twisted, and folded into intricate Calabi-Yau shapes, which we'll explore in Fact 2, or even stretched out like a vast, invisible landscape parallel to our own. So, what does this mean for us? If higher dimensions are real, they'd rewrite the rules of reality. Gravity's puzzling weakness could be because it's leaking into these dimensions. More on that in Fact 4. Quantum entanglement's spooky action at a distance might just be particles touching through a hidden dimension. Even black holes could be gateways to these realms. The craziest part, we might be bathed in higher dimensions every second without ever knowing. Ready to unravel more, because next we're diving into the bizarre geometric shapes that could be hiding right under your nose. Now let's zoom in on one of the most fascinating predictions of string theory, the hidden architecture of reality itself. Picture a tapestry woven with threads so fine they're invisible to the naked eye, yet their patterns dictate everything you see. That's the role of Calabi-Yau shapes, the six-dimensional geometric masterpieces that might be the hidden scaffolding of our universe. These shapes aren't just any random folds in space. They're solutions to equations so complex that even mathematicians struggle to visualize them. Named after the mathematicians Eugenio Calabi and Xing-Tung Yau, these structures are like the DNA of higher dimensions, tiny, curled-up spaces far smaller than an atom, where the extra dimensions of string theory hide. If you could shrink down to a subatomic scale, you might find these intricate shapes everywhere, twisting and turning in ways that defy our everyday intuition. So, why do these shapes matter? Imagine you're tuning a radio. Each slight turn of the dial changes the station you pick up. In a similar way, the vibrations of strings, those fundamental threads of reality we discussed earlier, are shaped by the geometry of these Calabi-Yau spaces. A string vibrating in one pattern might become an electron, while another pattern could give rise to a quark or a photon. The exact properties of every particle in the universe, their mass, their charge, even the forces they feel, could be determined by how these strings dance through the hidden folds of a Calabi-Yau shape. Here's where it gets even wilder. These shapes aren't just static backdrops, they're dynamic, possibly fluctuating in ways that could explain some of the deepest mysteries in physics. For instance, the vacuum of space isn't truly empty, it's seething with quantum energy. Some theories suggest this energy might be tied to the way Calabi-Yau shapes stabilize or shift at scales we can't yet observe. If these shapes were to flip into a new configuration, it could alter the very laws of physics in our universe, a cosmic reset button we'd never see coming. But how do we even begin to study something so vanishingly small? That's the catch. Current technology can't probe these scales directly, so physicists rely on the language of mathematics to map these shapes. Visualizing a six-dimensional object is impossible for our three-dimensional brains, but mathematicians can describe their properties like the number of holes or handles they contain, which in turn affect how strings behave. It's like deducing the shape of a locked room by listening to the echoes inside. The beauty of Calabi-Yau shapes lies in their potential to unify physics. If string theory is correct, these hidden geometries could bridge the gap between quantum mechanics and general relativity, the two pillars of modern physics that currently refuse to play nice. By understanding how dimensions curl into these shapes, we might finally crack the code of the universe's deepest layers. And here's a thought to leave you with. Right now, as you watch this, there could be an entire hidden dimension curled up inside every atom in your body, guiding the very fabric of reality. Next, we'll explore how these secret dimensions might not just be tiny hideaways, but gateways to entire parallel universes. Now, let's stretch our imaginations even further, because hidden dimensions might not just be tiny, curled-up spaces. They could be the very foundation of something far grander, the multiverse. Think of it like this. If Calabi-Yau shapes are the hidden scaffolding of our universe, then brains, short for membranes, are the cosmic neighborhoods where entire universes might exist side by side, separated by dimensions we can't perceive. Picture a loaf of bread. Each slice is a universe existing independently but stacked together in higher dimensional space. These slices are brains, vast, membrane-like structures floating in a higher dimensional bulk. Our entire universe, with all its galaxies and atoms, could be one of these brains, and right next to us, just a whisper away in an unseen dimension, there might be another brain, another universe with its own laws of physics, its own stars, even its own versions of you. Here's where it gets truly mind-bending. These brains aren't necessarily static. They could drift, collide, or even ripple like sheets in the wind. Some theories suggest that the Big Bang itself might have been the result of two brains smashing together, a cosmic collision so violent it birthed our universe. The energy from that impact could have been the spark that set everything in motion, and if brains can collide once, they could do it again, meaning our universe might not be the only one born from such an event. But how do we know any of this is possible? The math behind brain cosmology, a branch of string theory, suggests that gravity, the only force that might leak between dimensions, could be the key. If gravity is spread across multiple dimensions, its weakness in our universe makes sense. But here's the twist. If another brain drifted close to ours, the gravitational tug between them could leave traces we might detect: ripples in spacetime, anomalies in cosmic radiation, or even strange particle behavior. So far, no smoking gun has been found, but the search is on. And then there's the dark matter connection. Some physicists speculate that dark matter, the invisible stuff making up most of the universe's mass, might actually be ordinary matter from a neighboring brain. Its gravity could affect us, but because it's stuck in another dimension, we can't see or interact with it directly. It's like feeling the wind from a fan you can't see. You know it's there, even if it's hidden. The wildest part, if brains exist, the multiverse could be far stranger than just copies of our universe. Each brain might have entirely different physics. Some could have more dimensions, some fewer. Some might be bursting with life, while others are cold, empty voids. The possibilities are as vast as the dimensions themselves. So, the next time you look up at the night sky, remember, you might not just be gazing at stars. You could be peering out at a cosmic shoreline, with entire universes lying just beyond the horizon of perception. And as we push the boundaries of physics, who knows, we might one day find evidence that we're not alone in the grand expanse of higher dimensional space. Up next, we'll tackle one of the biggest puzzles in physics: why gravity is so weak compared to the other forces, and how hidden dimensions might hold the answer. Here's something that has puzzled scientists for decades. Gravity is shockingly weak compared to the other fundamental forces. Think about it. A tiny magnet can lift a paperclip, defying the entire gravitational pull of the Earth. So why is gravity, the force that holds galaxies together, so feeble on small scales? Hidden dimensions might hold the answer. Imagine gravity isn't confined to our four-dimensional universe. Instead, it could be spreading out into higher dimensions, thinning its influence in our familiar reality. Picture a drop of ink falling into a glass of water. In a small glass, the ink stays concentrated, strong, and vivid. But pour that same drop into a swimming pool, and it becomes almost invisible as it disperses. That's the core idea behind the leaking gravity theory. If gravity operates in extra dimensions, its strength in our world would be diluted, explaining why it feels so weak compared to electromagnetism or the nuclear forces. This isn't just wild speculation, it's a serious proposal rooted in string theory and brain cosmology. In these frameworks, our universe might be a three-dimensional brain floating in a higher dimensional space. While particles like electrons and quarks are stuck to our brain, gravity, which arises from the fabric of spacetime itself, could seep into the bulk of these extra dimensions. That's why it feels so much weaker here. Experimental physicists have been hunting for signs of this leakage. If gravity escapes into extra dimensions, its strength should deviate from Newton's predictions at extremely short distances smaller than a millimeter. Precision experiments with tiny, suspended weights have probed these scales, but so far, no definitive evidence has emerged. The Large Hadron Collider also scans for missing energy particles that might carry gravitational force into unseen dimensions, but the mystery persists. What makes this idea so compelling is that it solves two puzzles at once. First, it explains gravity's puzzling weakness. Second, it offers a way to reconcile quantum mechanics with general relativity, a major hurdle in modern physics. If gravity's true strength is actually much higher but spread across extra dimensions, The apparent mismatch between forces starts to make sense. Of course, not everyone is convinced. Some argue that if extra dimensions exist, they must be smaller than an atom's nucleus to avoid contradicting existing data. Others propose alternative explanations like modified gravity theories. But the notion that hidden dimensions could be stealing gravity's power remains one of the most elegant solutions on the table. So the next time you drop your phone and it falls to the floor, consider this: gravity's gentle tug might not just be a feature of our universe. It could be a clue whispering to us from dimensions beyond our sight. And if we're right, unlocking this secret could rewrite our understanding of reality itself. Now, let's turn the clock back nearly a century to explore one of the earliest ideas about higher dimensions, a theory that was bold, brilliant, and almost forgotten. Let's rewind to a time when the idea of hidden dimensions wasn't just a fringe concept, it was a revolutionary spark in the world of physics. Back in 1921, a little-known mathematician named Theodore Kaluza dared to suggest something extraordinary. What if there was a fifth dimension, not just an abstract idea, but a real physical dimension that could unite two of nature's most fundamental forces, gravity and electromagnetism? At first glance, Kaluza's proposal seemed almost magical. He took Einstein's equations of general relativity, which describe gravity in 4 dimensions, and extended them into 5. The result, electromagnetism, emerged naturally from the math, as if it had been hiding in plain sight all along. Picture a flashlight beam revealing a hidden message on a wall. What seemed like 2 separate phenomena suddenly appeared as different facets of the same deeper reality. Kaluza's work suggested that if we could step back into a higher dimensional perspective, the forces governing our universe might simplify into a single, elegant framework. But here's where things get even more fascinating. Kaluza's colleague, Oscar Klein, later refined the idea, proposing that this 5th dimension wasn't just a mathematical trick, it could be real, but curled up so tightly that we'd never notice it in everyday life. Think of a garden hose. From a distance, it looks like a simple line, one dimension, but up close, you see it's actually a cylinder with a circular dimension wrapped around its length. Klein argued that if the 5th dimension was similarly tiny, perhaps smaller than an atom, it would explain why we don't perceive it directly. For a brief moment, this Kaluza-Klein theory looked like it might unlock the secrets of the cosmos. But then progress stalled. The math was beautiful, but physicists struggled to find experimental evidence or extend the idea to other forces. Quantum mechanics was exploding onto the scene, stealing the spotlight with its strange, counterintuitive predictions. By the 1930s, Kaluza and Klein's work was pushed to the margins, a curious footnote in the history of physics. Yet, like a seed lying dormant in winter, the idea never truly died. Decades later, string theorists dusted off Kaluza-Klein's insights and realized they were holding a blueprint for something much bigger. String theory, which describes particles as tiny vibrating strings, required extra dimensions to make the math work. And guess what? Those dimensions had to be compactified, curled up, just like Klein had imagined. Suddenly, an old, forgotten idea became central to one of the most ambitious theories in modern physics. What's remarkable is how ahead of their time Kaluza and Klein were. They didn't have the tools or data we have today, but their intuition pointed toward a profound truth, that hidden dimensions might hold the key to unifying the forces of nature. Their story also reminds us that scientific breakthroughs often don't follow a straight line. Ideas can fade only to resurface when the time is right. Now, fast forward to today, and Kaluza-Klein theory is more relevant than ever. It's a cornerstone of higher dimensional physics, inspiring models that aim to explain everything from dark matter to the hierarchy of particle masses. So the next time you hear about extra dimensions, remember, it all started with a bold idea from a mathematician who dared to look beyond the visible. And speaking of bold ideas, let's jump into something even more mind-bending: the strange connection between quantum entanglement and hidden dimensions. Now, let's unravel one of the most baffling puzzles in quantum mechanics, a phenomenon so strange that even Einstein called it spooky action at a distance. Quantum entanglement, where particles instantly influence each other no matter how far apart they are, seems to defy the speed of light and our everyday intuition about space and time. But what if hidden dimensions hold the key to this mystery? Imagine two electrons born from the same quantum event, separated by light years in our three-dimensional universe. When you measure one, its entangled partner instantly knows the outcome, as if they're whispering secrets faster than light. This isn't just theoretical, it's been confirmed in countless experiments, leaving scientists scratching their heads. Here's where higher dimensions offer a possible solution. Some physicists propose that entangled particles aren't truly separated in the full geometry of the universe. Instead, they might be close in an extra, hidden dimension we can't perceive. Think of it like two ants crawling on opposite sides of a sheet of paper. To us, they're far apart, but if the paper curls into a tube, their paths could brush against each other in the third dimension. Similarly, entangled particles might brush past one another in a higher dimensional space, creating the illusion of spooky action in our limited 3D view. This idea isn't just speculation. String theory and holographic principle models suggest that what we perceive as vast distances in 3D space could be tiny gaps in higher dimensions. Picture a cosmic game of telephone where particles communicate through shortcuts in folded spacetime, like a wormhole for quantum information. Some versions of this theory even suggest that every particle in the universe might be subtly connected through these hidden threads, knitting reality into a single, inseparable whole. Critically, this perspective doesn't violate relativity's speed limit because no information is actually traveling through our 3D space. It's more like flipping a coin where both sides are predetermined to match, not because of signals flying between them, but because they're two parts of a deeper, higher dimensional structure. Of course, this remains speculative, but experiments are already probing the idea. For instance, if entanglement relies on hidden dimensions, certain quantum systems might exhibit subtle correlations that can't be explained by 3D physics alone. Future quantum computers or gravity wave detectors could one day spot these fingerprints of higher dimensional geometry. What's thrilling is how this ties back to Kaluza-Klein's old vision. Just as they saw forces unifying in higher dimensions, entanglement might reveal how particles remember their bonds beyond space and time. Whether or not the theory holds, it's a stunning reminder that the universe's deepest mysteries often point toward realities we've yet to imagine. And speaking of unseen realities, let's explore how hidden dimensions might explain another cosmic enigma: dark matter's elusive nature. Now, let's turn our attention to one of the biggest unsolved mysteries in cosmology, the enigma of dark matter. This invisible substance makes up roughly 85% of the universe's mass, yet it refuses to interact with light or ordinary matter in any way we can directly observe. So, where is it hiding? What if the answer lies not in our familiar 3 dimensions, but in unseen layers of reality just beyond our grasp? Here's a radical idea. Dark matter might be right beside us, woven into the fabric of parallel dimensions that overlap with our own. Imagine living in a house with invisible roommates. You can't see them, but sometimes you notice the furniture moving on its own. Dark matter could be the cosmic equivalent, existing in higher dimensional spaces that share the same gravitational address as our universe. Gravity, unlike other forces, might have the unique ability to stretch across these hidden dimensions, acting as the only tether between our world and theirs. To understand how this works, picture 2 sheets of glass pressed together. If ants lived on one sheet, they'd have no idea about the ants on the other, unless one group left behind sticky footprints that seeped through. In this analogy, gravity is those footprints, while electromagnetism and the nuclear forces stay trapped in their respective dimensions. Gravity's influence could bleed through, creating the ghostly pull we attribute to dark matter. This would explain why galaxies rotate as if they're heavier than they appear. Their visible stars are being tugged by unseen masses in adjacent dimensions. This theory isn't just science fiction. Models like Lisa Randall's warped extra dimensions suggest that gravity's unusual weakness compared to other forces might be because it's diluted across multiple dimensions. In our 3D slice of reality, we'd only perceive a fraction of its full strength, while the rest operates in realms we can't access. Remarkably, this could solve two puzzles at once: why gravity is so feeble and why dark matter seems to interact with nothing but gravity. Experimental clues are already hinting at this possibility. Take the Bullet Cluster, where two colliding galaxies left their dark matter shadows visibly separated from ordinary matter. If dark matter were merely a strange particle in our dimension, why wouldn't it collide like everything else? But if it's anchored in a parallel dimension, it could pass through our universe like a phantom, leaving gravity as its only trace. Critics argue we should exhaust all 3D explanations first, and they're right to be cautious. But the hidden dimension hypothesis offers something unique: testable predictions. If dark matter resides in higher dimensions, certain subtle gravitational anomalies like unexpected lensing patterns around galaxy clusters might eventually reveal its extra-dimensional nature. Future telescopes like the European Space Agency's Euclid mission could spot these telltale distortions. What's fascinating is how this ties back to string theory's curled-up dimensions. If dark matter particles are vibrations in these tiny, hidden geometries, they'd be everywhere yet undetectable by conventional means. It's a humbling thought. The majority of the universe's mass might be right under our noses, just folded into dimensions too small or too twisted for us to perceive. As we ponder this, another question arises: could dark energy, the mysterious force accelerating the universe's expansion, also have roots in these hidden realms? But that's a puzzle for another day. For now, the takeaway is clear: dark matter's invisibility might not be a flaw in our observations, but a signpost pointing to dimensions we've yet to fully explore. And if that's true, the universe is far stranger and far more layered than we ever imagined. Now, let's take a step into what might be the most mind-bending idea yet: the holographic principle. Picture this: everything you see, touch, and experience in our three-dimensional universe could actually be a projection from a two-dimensional surface at its outer edge. It's like staring at a hologram where a flat image creates the illusion of depth. But here's the twist: this isn't science fiction. It's a serious theory that some physicists believe could unlock secrets about hidden dimensions and the very fabric of reality. The idea originated from studying black holes, those cosmic vacuum cleaners where gravity is so intense that not even light can escape. When scientists calculated the amount of information a black hole could hold, they stumbled onto something unexpected. The data didn't scale with the black hole's volume, the way you'd expect in a 3D world, but instead with its surface area, as if the information was stored on a 2D boundary. This bizarre discovery led to a radical proposal. What if our entire universe operates the same way? Think of it like a movie projected onto a screen. The images appear to have depth, but all the information needed to create them is encoded in the flat, two-dimensional film. Similarly, the holographic principle suggests that the 3D universe we perceive, the stars, planets, even your morning coffee, might just be a detailed projection from information embedded in a 2D surface at the edge of space. That means every event, every particle, every law of physics could be written in a kind of cosmic code on this distant boundary, with our reality unfolding as a holographic interpretation of that data. But how does this connect to hidden dimensions? If the universe is a hologram, the extra dimensions predicted by string theory might not be additional spaces in the traditional sense. Instead, they could be part of the underlying information structure, like the pixels and algorithms that make a digital hologram work. We can't access this data directly, just as you can't reach into a movie screen to touch the film reel. Yet, these hidden layers could dictate the rules of our 3D experience, from the behavior of quantum particles to the curvature of spacetime itself. This gets even wilder when you consider quantum entanglement, where particles instantly influence each other across vast distances. In a holographic universe, this spooky action at a distance might make perfect sense. If entangled particles are actually linked at the 2D boundary where all information is stored, their connection wouldn't need to traverse 3D space. They'd be side by side in the code, even if they're light years apart in the projection. Critics argue that the holographic principle is still speculative, and they're right. We don't have direct evidence yet, but experiments like the Fermi Lab holometer have tried to detect quantum fuzziness, tiny vibrations that could hint at our universe's pixelated holographic nature. So far, no luck, but the search continues. What's captivating is how this idea flips our understanding of reality. If true, the cosmos isn't just hiding extra dimensions. It might be a shadow play with a real story written in a language of dimensions we can't see. It challenges us to ask, are we the actors or just the hologram? And if so, what or who is holding the projector, shifting our focus from mind-bending theories to hard science? Let's dive into how physicists are actively hunting for hidden dimensions, not with telescopes, but with the most powerful machine ever built, the Large Hadron Collider. Nestled beneath the Franco-Swiss border, this 17-mile ring of supercooled magnets smashes protons together at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. And here's the kicker. It might be our best shot at catching a glimpse of extra dimensions. The strategy is ingenious. When particles collide inside the LHC, their energy should always add up according to the laws of physics. But if extra dimensions exist, some of that energy could vanish literally. How? Imagine throwing a ball into a curtain, only for it to disappear halfway through. In this case, particles produced in collisions might carry energy into higher dimensions we can't see, leaving detectable gaps in the measurements. Scientists call this missing transverse energy, and it's one of the key signatures they're scouring the data for. Now you might wonder, if we're smashing particles with enough energy to recreate the early universe, why haven't we found definitive proof yet? The answer lies in the scale. Some theories suggest extra dimensions could be curled up incredibly small, far tinier than even the LHC can probe directly. Others propose they might exist at larger scales but remain just outside our current energy thresholds. Think of it like trying to hear a whisper in a thunderstorm. The signal might be there, but the noise is overwhelming. But here's why the search is far from over. The absence of evidence isn't evidence of absence. The LHC has already ruled out certain models of extra dimensions, narrowing the possibilities. And with upgrades boosting its power, future collisions could reach energies where subtle hints, like microscopic black holes or exotic particles, might finally emerge. These wouldn't be the planet-swallowing black holes of sci-fi. They'd evaporate instantly via Hawking radiation, leaving behind a telltale burst of energy. What makes this hunt so thrilling is that it's a 2-for-1 deal. Finding missing energy wouldn't just confirm hidden dimensions, it could also solve the mystery of gravity's weakness. If gravity leaks into extra dimensions, as some theories suggest, detecting its footprint in particle collisions would be the smoking gun. So while we haven't struck gold yet, the LHC isn't just a microscope for the universe, it's a time machine, a dimension detector, and maybe, just maybe, the key to rewriting physics as we know it. The next big discovery could be one collision away. Now let's turn our attention to one of the most tantalizing possibilities in the search for hidden dimensions, the potential creation of microscopic black holes right here on Earth. If extra dimensions exist at certain energy scales, the Large Hadron Collider might not just reveal missing energy, it could actually produce fleeting black holes smaller than an atom. Here's how this strange phenomenon would work. In our familiar four-dimensional universe, the energy required to create a black hole is unimaginably high, far beyond what any human-made collider could achieve. But if gravity operates differently in higher dimensions, as some versions of string theory suggest, the threshold for forming these tiny cosmic curiosities could drop dramatically. Imagine gravity as a force that's normally diluted by spreading thinly across our four dimensions. But in a universe with extra dimensions, gravity might become concentrated, making it powerful enough to warp space into microscopic black holes at achievable collision energies. The behavior of these hypothetical black holes would be nothing like their massive counterparts in space. Instead of devouring everything around them, they'd evaporate almost instantly through a process called Hawking radiation. Proposed by Stephen Hawking in the 1970s, this phenomenon suggests black holes slowly lose energy by emitting particles, a gradual fading that would happen at lightning speed for something so small. In fact, a micro-black hole created in the LHC might exist for less than a trillionth of a second before dissolving into a shower of detectable particles. This makes them an ideal test for string theory. If scientists observe the telltale burst of particles matching Hawking's predictions, it wouldn't just confirm extra dimensions, it would validate an entire framework that has remained purely mathematical for decades. The signature would be unmistakable, a sudden, symmetric spray of particles with no conventional explanation, like fireworks erupting from an invisible center. Now, skeptics might ask, if the LHC hasn't created black holes yet, does that rule out extra dimensions? Not necessarily. Their absence could mean extra dimensions are either smaller or larger than the scales the LHC currently probes. Some theories suggest we'd need collision energies 10 trillion times higher to produce them, far beyond our current technology. But even null results help physicists refine their models, ruling out certain configurations of hidden dimensions while guiding future experiments. What makes this hunt so thrilling is the dual payoff. Discovering micro-black holes wouldn't just revolutionize our understanding of gravity, it would bridge quantum mechanics and general relativity, two frameworks that have stubbornly resisted unification for a century. Every collision at the LHC isn't just a recreation of the universe's infancy, it's a potential doorway to dimensions we've never seen, waiting just beyond the edge of perception. So while these cosmic pinpricks remain hypothetical, their detection would be one of the greatest scientific breakthroughs in history, a whisper from the hidden architecture of reality itself. Moving from the cutting-edge experiments of today, let's rewind to a pivotal moment in theoretical physics, when the math itself demanded dimensions beyond imagination. Bosonic string theory, one of the earliest attempts to unify quantum mechanics and gravity, threw physicists a curveball. The equations didn't just suggest extra dimensions, they insisted on 26 of them. At first glance, this seems absurd. Why would nature need 26 dimensions when our everyday experience fits neatly into 4? The answer lies in the delicate balance required to make the math work. In the 1970s, physicists discovered that for string vibrations, the tiny loops or filaments theorized to be the universe's fundamental building blocks, to behave consistently, they needed 26 dimensions to avoid mathematical contradictions. Without this precise number, the equations predicting particle behavior would break down, producing nonsensical results like negative probabilities or infinite energies. Think of it like tuning a guitar. If even one string is slightly off, the entire chord sounds wrong. Similarly, bosonic strings required 26 dimensions to stay in tune with quantum rules. This wasn't a choice, it was a mathematical necessity, but here's the twist. While the theory worked mathematically, it had a glaring flaw. It couldn't account for fermions, the particles that make up matter. Bosonic strings only described force-carrying particles, leaving half the universe's ingredients unexplained. This limitation led to a major refinement: superstring theory. By introducing supersymmetry, a concept pairing every boson with a Fermion partner, physicists trimmed the dimensional requirement from 26 down to 10. Suddenly, the theory could describe all known particles, not just forces. Later, Edward Witten's M-theory expanded the framework further, proposing an 11th dimension that unified competing string theories into a single, elegant structure. What's fascinating about these numerical shifts isn't just the reduction, it's how they reveal physics' guiding principle: elegance through constraint. Like a sculptor chiseling away excess marble, theoretical physicists use mathematical consistency to carve out plausible models of reality. The journey from 26 to 11 dimensions wasn't a retreat, it was progress, showing how tighter constraints often lead to deeper truth. Today, bosonic string theory remains a historical footnote, but its legacy is profound. It demonstrated that higher dimensions aren't just speculative, they're sometimes the only way to make the math coherent. And while we've yet to confirm whether 10, 11, or any extra dimensions exist, the very fact that math demands them keeps theorists searching for clues in particle colliders, cosmic radiation, and even the fabric of spacetime itself. After all, if history teaches us anything, it's that the universe rarely conforms to human intuition, but it always obeys the numbers. Now, let's venture into one of the most mind-bending ideas yet. What if time itself isn't just a ticking clock but a tapestry woven by hidden dimensions? We're used to thinking of time as a straight line moving inexorably from past to future. But what if that's just a shadow of something far more complex happening in higher dimensional space? Imagine time as a river. In our everyday experience, it flows in one direction, just like a river's current. But in higher dimensions, that river might branch, twist, or even loop back on itself. Some physicists speculate that what we perceive as the arrow of time, the relentless march from order to disorder described by entropy, could actually emerge from interactions between dimensions. Think of it like a movie reel. From our limited 3D perspective, we only see one frame at a time, creating the illusion of linear progression. But in higher dimensions, the entire reel might exist at once, with past, present, and future stacked together like pages in a book. This idea ties closely to thermodynamics, the study of energy and disorder. Entropy, the measure of chaos in a system, always increases over time. That's why your coffee cools down and ice melts. But here's the twist: entropy might not be fundamental. Instead, it could be a byproduct of how our 3D universe slices through higher dimensional reality. Picture a loaf of bread. Each slice is a moment in time, but the loaf itself exists all at once. The increasing entropy we observe could simply be how we experience the structure of that higher dimensional loaf. Even stranger, some theories suggest that higher dimensions might store possibilities we perceive as past or future. In quantum mechanics, particles exist in superpositions, multiple states at once until measured. Similarly, time's flow could be a projection of countless possibilities playing out in dimensions beyond our perception. This isn't science fiction. Nobel Prize winner Roger Penrose proposed that the Big Bang's low-entropy state, a puzzle for physicists, might be explained by a higher dimensional boundary condition, a sort of cosmic reset shaped by geometry we can't yet see. So why does time feel so rigid to us? One compelling answer lies in the way dimensions interact. Just as a 2D creature can't perceive the third dimension's depth, our 3D plus time perspective might blind us to time's true nature. Experiments with quantum gravity hint at this. In certain models, spacetime behaves like a fluid near black holes, suggesting that time's flow could thicken or thin based on dimensional geometry we don't yet understand. This isn't just theoretical musing. If time is a higher dimensional phenomenon, it could solve paradoxes like time travel. Want to revisit the past? In higher dimensions, the past might not be behind us but simply accessible via a path we can't traverse in 4D. Wormholes, often depicted as shortcuts through spacetime, might require extra dimensions to remain stable, avoiding the infinite energies that make them implausible in 4D alone. The implications are staggering. If time is a shadow of higher dimensional physics, then free will, destiny, and even consciousness might operate on a stage far grander than we've imagined. It's a humbling reminder that our perception of reality is limited not by the universe's rules, but by the dimensions we're trapped in. And just as fish might not comprehend the concept of air, we might be missing the full picture of time itself. So the next time you glance at a clock, remember, those ticking seconds could be threads in a fabric stretching across dimensions we're only beginning to dream of. The mystery of time isn't just about what's next, it's about where and how many wheres are hidden beyond our view. Now, let's take a step into uncharted territory where the mysteries of the mind collide with the enigma of hidden dimensions. Could consciousness itself be a bridge to realms beyond our ordinary perception? This isn't just wild speculation. Some of the boldest theories in physics and philosophy suggest that our inner experience, the very essence of what it means to be, might be intertwined with the fabric of higher dimensional space. First, consider panpsychism, the idea that consciousness isn't exclusive to brains but is a fundamental feature of the universe, like mass or charge. If that's true, where does it reside? One provocative answer lies in the tiny, curled-up dimensions of string theory, the Calabi-Yau shapes we discussed earlier. These intricate geometric forms, far smaller than atoms, could be more than just mathematical curiosities. They might encode the vibrations of consciousness itself. Picture a piano string. When plucked, it produces a note. Similarly, the complex geometry of these hidden dimensions might resonate in ways that give rise to subjective experience, what philosophers call qualia, the raw fields of colors, sounds, and emotions. This idea gets even stranger when you examine quantum mechanics. At the subatomic level, particles exist in probabilities until observed. The act of measurement, often tied to consciousness, collapses these possibilities into a single outcome. Some interpretations, like the von Neumann-Wigner hypothesis, suggest consciousness plays an active role in shaping reality. Now layer on hidden dimensions. What if the collapse of the quantum wave function isn't happening in our 3D world but in a higher dimensional space? Our brains might be like radios, tuning into signals broadcast from dimensions we can't see. Then there's the hard problem of consciousness, coined by philosopher David Chalmers. Why does physical processing in the brain feel like anything at all? Traditional neuroscience struggles here, but higher dimensions offer a tantalizing clue. Imagine your mind isn't confined to your skull. Instead, it's a projection, a 3D shadow of a more complex, multidimensional process. Think of a flatlander seeing only cross-sections of a sphere. Similarly, our conscious experience could be a limited slice of a richer, dimensional tapestry. Even near-death experiences hint at this. People report vivid, non-local awareness floating outside their bodies, seeing beyond visual barriers. While controversial, these accounts align with theories where consciousness unfurls into higher dimensions during extreme states. The brain might act as a filter, narrowing our perception to 3D survival, but under stress that filter could weaken. Of course, this is speculative. Critics argue it's untestable, sliding into metaphysics, but science marches forward by asking impossible questions. If hidden dimensions shape gravity and quantum fields, why not consciousness? The Calabi-Yau spaces governing particle properties might also orchestrate the symphony of subjective experience. So where does this leave us at the frontier of knowing? Whether consciousness is a dimensional phenomenon or not, the mere possibility reshapes how we see ourselves. You're not just a bag of atoms. You might be a multidimensional entity peering through a keyhole we call reality. And that keyhole could be wider than we ever dreamed. Now, let's journey back in time where ancient wisdom and modern science might just be speaking the same cosmic language. Long before particle colliders and string theory, civilizations across the globe described realities that eerily mirror today's cutting-edge physics. Could their sacred texts and myths have been intuitive maps of hidden dimensions? Take Hindu cosmology, for example. The Puranas describe a universe structured in layers, like an infinite stack of realms, each with its own laws and beings. Sound familiar? It's strikingly close to the brain concept in modern physics, where parallel universes float like sheets in higher dimensional space. The Rig Veda even hints at a golden womb, Hiranyagarbha, a primordial singularity from which all dimensions unfold. Then there's the concept of lokas, often translated as worlds or planes, which some scholars interpret as vibrational frequencies, akin to how Calabi-Yau shapes in string theory vibrate to create particles. The ancient sages might not have had the math, but their metaphors align uncannily with the idea of compactified dimensions. Shift to the Jewish mystical tradition of Kabbalah. Its central symbol, the Tree of Life, maps reality through 10 Sephirot emanations or dimensions of divine energy. Each Sephirah governs aspects of existence, from wisdom to physicality, interconnected by paths representing dynamic relationships. Modern physicists might see a parallel in M-theory's 11 dimensions, where membranes and strings interact across a multidimensional landscape. The Kabbalistic idea of tzimtzum, divine contraction to make space for creation, even echoes theories about higher dimensional fields collapsing to form our observable universe. But the connections don't stop there. Tibetan Buddhism speaks of bardos, transitional states between dimensions of consciousness, much like quantum superpositions where particles exist in multiple states until observed. Indigenous Australian Dreamtime stories describe a timeless, multidimensional reality where ancestors shaped the world through songlines, cosmic vibrations that resonate with string theory's musical universe. Even Plato's allegory of the cave, where shadows hint at a deeper reality, mirrors the holographic principle's claim that our 3D world is a projection. So how did ancient cultures know these concepts? One theory points to altered states. Shamans and mystics, through meditation or entheogens, might have glimpsed higher dimensional truths encoded in the fabric of perception. Neuroscientist Rick Strassman's DMT studies note subjects reporting encounters with entities in geometric, hyperdimensional spaces, descriptions that overlap with Calabi-Yau landscapes. Alternatively, these myths could be humanity's collective intuition, a symbolic language for truths we're now uncovering mathematically. Skeptics argue it's coincidence or projection, that we're cherry-picking myths to fit modern theories. But the consistency across isolated cultures is hard to ignore. Whether by revelation or intuition, these traditions seem to have brushed against dimensions science is only beginning to chart. What's mesmerizing is the duality here. Our most advanced physics and oldest spiritual systems might be converging on the same cosmic blueprint. Perhaps hidden dimensions aren't just a futuristic discovery, they've been whispered in humanity's oldest stories all along. And if that's true, it begs a thrilling question: what other cosmic secrets are buried in the annals of ancient wisdom? Next, we'll turn our gaze to the subatomic world, where ghostly particles might be slipping between dimensions right under our noses. The mystery of dimension-hopping neutrinos awaits. Now, let's zoom in on one of the universe's most elusive travelers, the neutrino. These ghostly particles, nearly massless and barely interacting with matter, might hold clues to hidden dimensions in their bizarre behavior. Picture this: a neutrino born in the heart of the Sun starts its journey as one type, say an electron neutrino, but by the time it reaches Earth, it's morphed into a muon or tau neutrino. This phenomenon, called neutrino oscillation, flummoxed scientists for decades. Why? Because it suggests these particles are playing by rules we don't fully understand, and extra dimensions could be part of the game. Here's the puzzle. According to quantum mechanics, a particle's flavor, its type, should stay constant unless something interferes. but neutrinos oscillate as they travel, as if they're sampling different identities. One tantalizing explanation: they're not just moving through our three-dimensional space. Imagine a neutrino as a ball bouncing between two rooms separated by a thin wall, our universe and a hidden dimension. Each bounce could tweak its properties, making it switch flavors in ways that defy conventional physics. The math gets even wilder. Some theories propose that what we perceive as neutrino mass might actually be a shadow of higher dimensional activity. In our world, a neutrino's mass seems tiny, but in extra dimensions it could have more heft that bleeds into our reality. This is like hearing a faint echo of a shout from another room. The full sound is happening elsewhere, but we only catch whispers. Experiments like MINOS and IceCube have detected anomalies in neutrino behavior that don't fit the standard model. Could these gaps be hints of dimensions beyond our perception? Then there's the speed mystery. In 2011, the OPERA experiment initially reported neutrinos traveling faster than light, a finding later debunked by a loose cable. But what if the error masked a subtler truth? Hypothetical sterile neutrinos, which don't interact with any known force except gravity, might shortcut through extra dimensions, appearing to flirt with light speed limits. These hypothetical particles could be the universe's ultimate dimension hoppers, slipping between branes like cosmic stealth agents. Think of neutrinos as cosmic detectives leaving faint trails. Their oscillations, masses, and speeds might be encoded messages about the fabric of spacetime. Future experiments like the Deep Underground Neutrino Experiment (DUNE) could crack this code by firing neutrinos through 800 miles of Earth's crust. If their flavors shift in unexpected ways, we might glimpse the fingerprints of extra dimensions. So why does this matter? Because neutrinos are everywhere. Trillions pass through you every second. If they're interacting with hidden dimensions, it means these realms aren't just abstract math. They could be shaping the universe in ways we're only starting to sense. From ancient myths to ghostly particles, the threads of higher dimensions keep weaving through our reality. And if neutrinos are the key, we might be on the verge of unlocking one of spacetime's best-kept secrets. Next, we'll uncover how nature's most intricate patterns, fractals, might be blueprints for dimensions we can't yet see. Get ready to rethink reality's hidden geometry. Now, let's take a step into nature's most mesmerizing patterns, where the boundaries between dimensions might just blur. Fractals, those infinitely intricate shapes repeating at every scale, could be more than just mathematical curiosities. They might be whispers of hidden dimensions woven into the fabric of our universe. Picture a fern leaf. Zoom in on one tiny segment, and it looks nearly identical to the whole leaf. This self-similarity isn't just a quirk of biology, it's a hallmark of fractals, and some physicists suspect it's a clue to how higher dimensions express themselves in our 3D world. Fractal math bends the rules of classical geometry. While a circle or square lives neatly in whole number dimensions, fractals like the Mandelbrot set exist in fractional dimensions somewhere between 2D and 3D. This strange in-betweenness hints at a deeper truth. Fractals might be shadows of structures that truly live in higher dimensions, projected into our reality like a 3D hologram flattened onto a 2D screen. Imagine crumpling a piece of paper over and over. From a distance, it looks like a smooth sheet, but up close, its folds reveal layers upon layers of complexity. Could spacetime itself harbor similar hidden folds, with fractals as their fingerprints? Nature adores fractals. Lightning bolts branch in fractal patterns, lungs use fractal airways to maximize surface area, and galaxies cluster in fractal-like distributions across the cosmos. Even the human brain's wrinkles mirror fractal geometry. This ubiquity raises a tantalizing question. Are these patterns accidental, or do they reflect a deeper, multidimensional architecture? Some theories propose that fractal networks, like the branching veins of a leaf, might be efficient ways for higher dimensional energy or information to flow into our 3D world. Think of a tree's roots spreading underground. In a higher dimension, those roots might connect to structures we can't see, trading nutrients or data across dimensional membranes. Here's where it gets wild. Quantum gravity researchers have explored fractal spacetime as a way to unify Einstein's relativity with quantum mechanics. In this view, spacetime at the tiniest scales isn't smooth but fractal, a foamy, endlessly complex web. This could explain why particles pop in and out of existence in quantum foam. They're dipping into fractal-linked dimensions. String theory, too, finds fractals useful. The Calabi-Yau shapes that define extra dimensions often exhibit fractal-like properties, suggesting that the curled-up dimensions might not be simple loops but infinitely detailed fractal labyrinths. Even black holes might hide fractal secrets. The event horizon, the point of no return, could have a fractal structure when viewed at Planck-scale resolutions. Some models suggest that information swallowed by a black hole gets scrambled into fractal patterns on its surface, a twist on the holographic principle where 3D events are encoded on a 2D boundary. If true, fractals might be the universe's way of packing infinite complexity into finite spaces, a trick that could apply to hidden dimensions too. So what does this mean for us? Fractals blur the line between math and reality, hinting that dimensions might not be rigid layers but fluid, interconnected realms. Next time you see a snowflake or a coastline's jagged edge, consider this: their beauty might not just be skin deep. They could be glimpses of a multidimensional universe, whispering its secrets in geometries we're only beginning to decode. Up next, we'll dive into the grand unifying idea that ties all these threads together. M-theory's bold vision of an 11th dimension where the fabric of reality might truly begin. Now, let's pull back the curtain on one of the most ambitious ideas in modern physics, a theory so powerful it could be the key to unlocking the universe's deepest secrets. Welcome to M-theory, where the 11th dimension isn't just a mathematical curiosity but the stage upon which all reality might dance. Back in the 1990s, physicist Edward Witten made a stunning breakthrough. He realized that the 5 competing versions of string theory weren't rivals at all. They were different pieces of a much larger puzzle. By introducing an 11th dimension, Witten revealed that these theories were simply different angles of a single, unified framework, M-theory. The M stands for mystery, magic, or even membrane, depending on who you ask, and that ambiguity hints at just how revolutionary this idea truly is. So what does an 11th dimension actually mean? Imagine our familiar 4 dimensions: length, width, height, and time as just the beginning. String theory had already proposed 6 additional tiny, curled-up dimensions, but M-theory goes further. It suggests that the 11th dimension isn't small or hidden. Instead, it's vast, stretching far beyond our perception, and it's home to colossal structures called branes, short for membranes. These aren't the flimsy sheets you might picture. Think of them as immense, dynamic surfaces floating in the higher dimensional expanse, each potentially hosting an entire universe. Here's where it gets mind-bending. Our universe, with its galaxies, stars, and planets, might exist on just one of these branes, like a single page in an infinite cosmic book. Other branes could harbor parallel universes, each with their own laws of physics, forever separated from us by the higher dimensional void. But sometimes these branes might collide. When they do, the energy released could spark a big bang, birthing a brand new universe. That's right, the origin of everything we know might just be the aftermath of 2 higher dimensional worlds brushing against each other. M-theory doesn't just stop at explaining universes, it reshapes how we think about reality itself. Take gravity, for example. In this framework, gravity's puzzling weakness in our universe makes perfect sense. While other forces, like electromagnetism, are confined to our brain, gravity could leak into the 11th dimension, diluting its strength from our perspective. This elegantly solves one of physics' biggest headaches without inventing new particles or forces. But how do we test something so abstract? Enter the brain world scenario. If our universe is a brain floating in higher dimensional space, particles like gravitons, the hypothetical carriers of gravity, might occasionally escape into the bulk, the space between brains. Scientists are hunting for evidence of this in particle colliders, watching for tiny discrepancies in energy that could signal gravity's extra-dimensional adventures. While no smoking gun has been found yet, the search itself pushes the boundaries of what we thought possible. M-theory also offers a fresh take on black holes. Instead of singularities, infinitely dense points of no-return black holes might be higher-dimensional objects intersecting our brain. Their event horizons could be shadows of intricate, multidimensional structures, and the information they swallow might not vanish but instead spread across the brain's surface like ink soaking into paper. Now here's the real kicker. M-theory doesn't just add an 11th dimension, it suggests that strings, the fundamental building blocks in string theory, might actually be one-dimensional slices of something even more fundamental, two-dimensional membranes vibrating in the 11th dimension. Picture a guitar string vibrating to create different notes. Now imagine that string is the edge of a drumhead wobbling in an unseen dimension. The music it makes could be the very fabric of reality. Critics argue that M-theory is still largely mathematical, lacking experimental proof, but its power lies in its potential. It bridges Einstein's relativity and quantum mechanics, unifies all known forces, and even offers a plausible mechanism for the multiverse. For now, it remains a dazzling hypothesis, one that paints the cosmos not as a static backdrop, but as a dynamic, multidimensional tapestry forever unfolding. So the next time you gaze up at the night sky, remember this. What we see might just be a sliver of existence, a shadow cast by realities dancing in dimensions beyond our own. And as we peel back those layers, who knows what wonders await? Now, let's take a detour from the cosmos and turn inward to the mysterious landscapes of our own minds. Dreams have long baffled scientists and philosophers alike, with their surreal narratives and physics-defying logic. But what if these nightly adventures aren't just random firings of neurons? What if they're glimpses into hidden dimensions woven into the fabric of our subconscious? Consider the way dreams operate. Time bends, moments stretch into eternities or collapse in an instant. Spaces shift without warning. You might step through a door and find yourself in a completely different world. These aren't just quirks of imagination. Some theorists propose that dreams could be our brain's way of processing higher dimensional information, like a radio tuning into frequencies beyond our waking perception. Neurochemistry offers a fascinating clue. Studies on dimethyltryptamine DMT for short reveal striking parallels. This powerful compound, naturally produced in small amounts by the human brain, induces vivid, dreamlike states even in waking life. Subjects report encounters with intricate geometric realms and entities that feel hyper-real, as if they've tapped into a dimension just beyond ordinary sight. The overlap between DMT experiences and dreams has led some researchers to speculate, could our brains be hardwired to access these hidden layers under certain conditions? Then there's the architecture of dream spaces. Ever tried to run in a dream only to move in slow motion, or encountered a staircase that loops endlessly, defying gravity? These impossible structures resemble the kind of warped geometries predicted by higher dimensional physics. In a three-dimensional world, such distortions wouldn't make sense, but in a space with extra dimensions, they might be perfectly logical. The holographic principle adds another layer. If our universe is a projection from a two-dimensional surface, as some theories suggest, then dreams might be fragments of that underlying code, glitches or echoes of the deeper reality. Imagine your brain as a receiver, occasionally picking up signals from the cosmic source file, reassembling them into the surreal narratives we experience as dreams. Of course, mainstream neuroscience leans toward more conventional explanations, like memory consolidation or emotional processing. but even here there's room for wonder. The brain's default mode network, the system active during daydreaming and self-reflection, shares uncanny similarities with the states induced by psychedelics or deep meditation. These altered states often dissolve the boundaries of time and space, much like dreams, hinting at a shared mechanism that might transcend ordinary perception. Skeptics argue that attributing dreams to higher dimensions is speculative at best. Yet the question remains, why do these experiences feel so profoundly real to so many? Whether it's a biological artifact or a peek behind the cosmic curtain, dreams challenge our understanding of reality in ways that parallel the mysteries of theoretical physics. So the next time you wake up from a dream that defies logic, ask yourself, was it just your mind playing tricks, or were you, for a fleeting moment, navigating the hidden dimensions that shape our universe? The answer might lie somewhere in the space between neuroscience and the cosmos, waiting to be unraveled. But here's a twist that might reshape how we picture hidden dimensions. While most theories assume extra dimensions are vanishingly small, curled up into intricate Calabi-Yau shapes a billion times tinier than an atom, physicist Lisa Randall proposed something radically different. What if at least one extra dimension isn't microscopic at all? What if it's large, not just large in quantum terms, but wide enough to span millimeters, a cosmic highway right under our noses? Randall's groundbreaking large extra dimension hypothesis flips the script on traditional string theory. Instead of relying on tiny, convoluted geometries to explain why we don't perceive extra dimensions, she suggests that one of them could be many orders of magnitude larger, yet still invisible to us. How? Imagine our entire universe is a three-dimensional brain, short for membrane, floating within a higher dimensional space. Gravity, unlike other forces, could leak off our brain and into this larger dimension, which would explain why it feels so weak compared to electromagnetism or the nuclear forces. This idea isn't just wild speculation, it tackles one of physics' biggest puzzles, the hierarchy problem. In simple terms, gravity is inexplicably feebler than other forces. If all forces originate from the same cosmic rules, why is gravity 10 to the power of 36 times weaker than electromagnetism? Randall's model offers an elegant fix. If gravity dissipates into a large extra dimension, its strength in our 3D world would appear diluted, like sunlight spreading across a vast room. Meanwhile, other forces remain stuck to our brain, maintaining their intensity. The math behind this is mind-bending yet beautiful. Randall and her collaborator Raman Sundram showed that warped geometry, think of space itself curving sharply near our brain, could naturally trap particles here, preventing them from sensing the extra dimension. But gravity, which depends on the shape of spacetime itself, would feel the full structure, including the large dimension. This warping effect could explain why we don't notice the extra space in daily life, even if it's millimeters wide. Unlike Calabi-Yau shapes, which require complex equations to hide dimensions, Randall's warped geometry achieves the same goal with startling simplicity. Experimentalists have eagerly tested this idea. If large extra dimensions exist, particle colliders like the Large Hadron Collider might produce miniature black holes or exotic particles called gravitons that briefly escape into the higher dimension before snapping back. While no definitive evidence has emerged yet, the absence of these signals doesn't rule out Randall's model. It might just mean the dimension is slightly smaller than predicted, or that we need more powerful tools to probe it. Critics argue that a millimeter-scale dimension should have left traces in precision gravity experiments, like deviations in Newton's law at tiny distances. So far, no such anomalies have been confirmed, but Randall counters that warping effects could suppress these signatures, making the dimension stealthier than expected. Others point out that her theory doesn't fully replace string theory but complements it, offering an alternative pathway to unify physics. What makes this hypothesis so compelling is its audacity. It challenges us to rethink not just where hidden dimensions might be, but how they interact with our reality. Maybe the cosmos isn't just a tapestry of tiny, curled-up threads. It could be a vast, layered construct where dimensions of vastly different scales coexist, each playing a unique role in the grand scheme. As we push the boundaries of colliders and quantum sensors, we might finally catch gravity red-handed, slipping into the shadows of a dimension we've overlooked, one that's been hiding in plain sight all along. Now let's tune into something truly extraordinary, the hidden symphony of the cosmos. If string theory is correct, the universe isn't just built on tiny vibrating strings, it might actually sing. These vibrations, dancing across hidden dimensions, could create a kind of dimensional resonance, a cosmic harmony that echoes through reality itself. Think of it like this: every particle in the universe, from quarks to galaxies, might be a note in a grand celestial composition. String theory suggests that the properties of particles, their mass, charge, even the forces they feel, are determined by how these tiny strings vibrate. Just as a guitar string produces different notes depending on its tension and length, cosmic strings could play different particles based on their vibrational patterns. But here's where it gets wild. Those vibrations might not be confined to our familiar 3 dimensions. They could ripple through higher dimensional spaces, creating harmonies we can't directly hear but whose effects shape everything around us. This idea isn't entirely new. Ancient philosophers like Pythagoras spoke of the music of the spheres, the belief that celestial bodies move in precise mathematical ratios, creating an inaudible cosmic melody. Fast forward to today, and modern physics might be giving that poetic idea a scientific backbone. Researchers have even explored connections between string theories, vibrations, and sacred geometry, the intricate patterns found in everything from snowflakes to galaxy clusters. These shapes, often tied to ratios in music like the Fibonacci sequence in a Nautilus shell, could hint at deeper dimensional harmonies. Then there's cymatics, the study of visible sound. When sand or liquid is placed on a vibrating plate, it forms intricate geometric patterns that change with frequency. Higher pitches create more complex designs, almost like a 2D shadow of the sound structure. Now imagine those patterns unfolding in higher dimensions. Could the universe's fundamental vibrations leave similar geometric imprints in the fabric of spacetime? Some theorists suggest that phenomena like quantum foam or the distribution of galaxies might reflect these hidden resonant structures, but how would we test this? One clue lies in the cosmic microwave background, the afterglow of the Big Bang. If hidden dimensions influence vibrational patterns, they might leave faint scars in this ancient light, like a fingerprint of higher dimensional physics. Others propose that advanced gravitational wave detectors could one day pick up subtle harmonies in spacetime itself, vibrations that betray the presence of extra dimensions. What's fascinating is how this bridges science and art. Composers like John Cage have experimented with translating cosmic data into music, turning asteroid orbits or quantum fluctuations into melodies. While these are artistic interpretations, they raise a provocative question. If we could hear higher dimensions, what would they sound like? Would dark matter hum in bass notes? Would quarks chirp like violins? The universe might be less like a silent machine and more like a vast, vibrating orchestra, one where dimensions we can't see or touch play the most profound chords. So next time you listen to a song, consider this. The music you enjoy is just a tiny echo of a far grander symphony, one composed not just in our world but in the hidden depths of reality itself. Whether through math, physics, or pure imagination, the idea of dimensional resonance invites us to experience the universe not just as a place to explore, but as a masterpiece to listen to. Now let's turn our attention to a concept that's as eerie as it is fascinating: the idea that higher dimensional objects could be casting shadows into our universe. Think about how a three-dimensional object like a hand casts a two-dimensional shadow on a wall. Now imagine something far stranger, objects from 4, 5, or even more dimensions casting faint, distorted imprints in our three-dimensional reality. These ghostly traces might explain some of the most perplexing mysteries in science today, from UFO encounters to the enigma of dark energy. Here's the wild part. If hidden dimensions exist, their inhabitants, or even inanimate structures, could intersect with our universe in ways we can't fully perceive. Just as a flatlander in Flatland wouldn't recognize a human hand except as a bizarre, shifting shadow, we might only catch glimpses of higher dimensional phenomena. These glimpses could manifest as fleeting distortions in gravity, unexplained energy signatures, or even objects that appear to move in ways that defy our known physics. Take dark energy, for example. This mysterious force is accelerating the expansion of the universe, yet no one knows what it actually is. Some theories suggest it might be the leakage of energy from higher dimensions, like a shadowy pressure seeping through the cracks of spacetime. Similarly, certain UFO sightings, especially those involving objects that seem to vanish or move with impossible agility, might be misinterpretations of higher dimensional objects passing through our reality. They wouldn't be alien spacecraft in the traditional sense, but rather fragments of a geometry we can't comprehend. Of course, the scientific community approaches these ideas with healthy skepticism. Extraordinary claims require extraordinary evidence, and so far, no definitive proof links UFOs or dark energy to hidden dimensions. But that doesn't stop physicists from creatively exploring the possibilities. After all, some of history's greatest breakthroughs started as wild speculation. The key is to balance open-mindedness with rigorous testing, because if higher dimensional shadows are real, they'd likely leave subtle but detectable traces. Consider black holes. These cosmic anomalies warp spacetime so severely that they might serve as natural windows into higher dimensions. Some models suggest that the bizarre behavior of matter near a black hole's event horizon could hint at unseen dimensional layers. Even more intriguing are quantum particles, which sometimes behave as if they briefly slip into or interact with other dimensions before snapping back into our observable universe. So while we shouldn't jump to conclusions, we also shouldn't dismiss the poetry of the idea. The universe has surprised us before, revealing realities far stranger than fiction. Whether these ghostly shadows are the key to unlocking dark energy, rewriting physics, or simply inspiring new questions, they remind us that the cosmos is vast, mysterious, and still full of secrets waiting to be uncovered. Who knows, the next great discovery might not come from looking deeper into our world, but from deciphering the faint whispers of dimensions beyond it. Now let's venture into one of the most mind-bending thought experiments in physics, the Boltzmann brain paradox, and see how it might intertwine with the mysteries of hidden dimensions. Imagine this: what if, instead of a full universe, a single, self-aware brain spontaneously popped into existence out of random quantum fluctuations? That's the essence of the Boltzmann brain, a hypothetical scenario that challenges our understanding of reality, consciousness, and even the nature of time itself. Here's where it gets even stranger. If hidden dimensions exist, could these floating, self-aware brains emerge not just in our familiar three-dimensional space, but within the folds of higher-dimensional quantum foam? Quantum foam is the turbulent, seething fabric of spacetime at the tiniest scales, where particles blink in and out of existence. In a universe with extra dimensions, this foam could be far more complex, offering new pathways for Boltzmann brains to form, and perhaps even interact with our reality in ways we can't yet fathom. Think of it like this: in our everyday world, the odds of a fully formed brain suddenly appearing are vanishingly small. But in the infinite expanse of higher dimensional space, where the rules of physics might be radically different, the probability could shift. Some theories suggest that in these extra dimensions, quantum fluctuations could be amplified, making freak events like Boltzmann brains far more likely. These brains wouldn't just be isolated curiosities, they might flicker in and out of our perception, leaving behind fleeting traces of consciousness or even influencing quantum systems in ways we mistake for random noise. Now let's tie this back to another puzzle. Why do we perceive a universe with such orderly structure instead of chaos? If Boltzmann brains are statistically more probable than a full, coherent universe, why aren't we all just disembodied brains hallucinating reality? One intriguing possibility is that hidden dimensions act as a stabilizing force. The extra dimensions could provide a framework that tips the scales toward structured reality, making the emergence of a stable universe like ours more likely than a swarm of disconnected, self-aware fragments. Of course, this is all speculative. The Boltzmann brain paradox is still a thought experiment, not an established fact, but it serves as a thrilling reminder of how much we don't yet understand about consciousness, quantum mechanics, and the deeper layers of reality. And if hidden dimensions are indeed part of the cosmic fabric, they might hold the key to resolving this paradox or deepening it even further. So the next time you ponder the nature of existence, ask yourself, are we the product of a vast, orderly universe, or could we, in some bizarre twist, be Boltzmann brain-esque entities ourselves, momentarily convinced of our own reality? The answer might lie not just in the dimensions we see, but in the ones we can't. Now let's shift our focus to a concept that has fascinated both scientists and storytellers for centuries: time travel. But we're not just talking about hopping into a DeLorean and zipping to the past. What if the key to unlocking time travel lies in the hidden dimensions we've been exploring? Here's the challenge with traditional four-dimensional time travel. In our familiar universe where time and space are intertwined, moving backward through time creates paradoxes. The classic example is the grandfather paradox. If you traveled back and prevented your grandfather from meeting your grandmother, you would never be born to make the trip in the first place. This violates causality, the principle that cause must always come before effect. It's a logical mess that makes time travel seem impossible within our four-dimensional framework. But hidden dimensions might offer a way out. Imagine if higher dimensions act like a bypass, allowing movement through time without running into these paradoxes. Some theories suggest that in a universe with extra dimensions, time isn't a single, linear path. Instead, it could branch across higher dimensional space, creating alternate timelines where changes in the past don't erase the future you came from. It's like taking a detour around a roadblock rather than smashing into it head-on. Wormholes are another fascinating piece of this puzzle. These hypothetical tunnels through spacetime could connect distant points in the universe or even different times. But here's the catch: wormholes are notoriously unstable. In our four-dimensional world, they would collapse instantly under their own gravitational pull. However, if extra dimensions exist, they might provide the scaffolding needed to keep a wormhole open long enough to traverse it. Think of it like trying to build a bridge with only two support beams. It would collapse. But add more beams from unseen directions and suddenly the structure holds. String theory offers a possible mechanism for this. Some models suggest that higher dimensional brains, theoretical membranes floating in a higher dimensional space, could stabilize wormholes by anchoring them in ways we can't perceive. If true, this would mean that time travel isn't just a sci-fi fantasy, but a potential feature of a multidimensional universe. Of course, there's still the question of how we'd access these higher dimensions. Right now, it's purely theoretical, but the idea itself reshapes how we think about time. Instead of a rigid arrow moving in one direction, time could be more like a vast, interconnected web, with hidden dimensions allowing pathways that avoid paradoxes altogether. So next time you daydream about visiting ancient Rome or witnessing the birth of a star, remember, the secret to time travel might not be in building a faster spaceship, but in uncovering the hidden dimensions that stitch the universe together. Who knows, the keys to the past and future could be closer than we think, just curled up in dimensions we can't yet see. Now let's venture into a mind-bending idea that ties hidden dimensions to one of the most debated theories of our time, the simulation hypothesis. What if our entire universe isn't the base reality, but instead a sophisticated program running on some higher dimensional computer? At first glance, this sounds like pure science fiction, but when you layer in the concept of extra dimensions, it takes on a startling new depth. Think about how we create simulations today, video games with entire worlds governed by coded rules, processed within the confines of our computers. Now imagine beings in a higher dimensional reality crafting simulations so advanced, they'd be indistinguishable from reality to the inhabitants inside. Here's where hidden dimensions add a fascinating twist. If our universe is a simulation, those extra dimensions we've been exploring might not just be physical. They could represent the processing architecture of the system running our reality. Just as a video game relies on unseen code and memory, our universe's hidden dimensions could be the scaffolding holding everything together behind the scenes. This idea might even explain some of the quirks we observe in physics. Take quantum mechanics, for example, the strange behavior of particles that seem to exist in multiple states until observed. Could this be a processing optimization in the simulation where resources are only allocated when needed? Similarly, cosmic glitches like anomalies in gravitational waves or unexplained particle behaviors might not be flaws in nature. They could be signs of the simulation's underlying code, hidden in dimensions we can't perceive. Some theorists take this further, suggesting that nested dimensions could explain the computational limits of such a simulation. Our universe operates with finite speed limits. Nothing travels faster than light, and quantum processes have resolution limits like Planck length. These constraints might reflect the processing power of the higher dimensional hardware. It's like how a game lags if you overload its engine. Our reality's rules could be artifacts of a system operating at capacity. But the most intriguing implication: if we're in a simulation, the creators might exist in dimensions beyond our own. Their reality could have physics entirely different from ours, with extra spatial dimensions allowing them to observe or interact with our universe in ways we can't comprehend, like a game developer tweaking variables from outside the program. Of course, this raises philosophical questions. If higher dimensions host our simulators, could they themselves be part of a deeper simulation? It's turtles all the way down, an infinite regression of realities within realities, each built upon dimensions the level below can't access. Whether you find this idea thrilling or unsettling, it undeniably reshapes how we view hidden dimensions. They might not just be unseen layers of space, they could be the hidden gears of the cosmic machine, the framework of a reality crafted by unknown hands. So the next time your phone glitches or you encounter a déjà vu moment, ask yourself, could this be a peek behind the curtain of our dimensional simulation? Now let's shift our gaze to one of the greatest cosmic mysteries of all: dark energy. This invisible force is causing the universe to expand at an accelerating rate, but no one knows exactly why. What if hidden dimensions hold the key to this enigma? Imagine dark energy as a ripple from a higher dimensional realm, subtly leaking into our universe and pushing galaxies apart. Here's how this wild idea works. In the early moments of the cosmos, something called inflation caused space to expand exponentially faster than the speed of light. This process was driven by a mysterious field that eventually faded, but what if dark energy is a faint echo of that same mechanism, now emerging from extra dimensions? Picture it like a lake with unseen springs beneath its surface. The water level rises not because of anything happening in the lake itself, but because of hidden sources feeding into it from below. Similarly, dark energy's push might come from higher dimensional fields gently pouring energy into our four-dimensional spacetime. This theory elegantly ties together two cosmic puzzles, inflation and dark energy, by suggesting they're two phases of the same dimensional phenomenon. During inflation, these higher dimensional fields were turbocharged, stretching the universe in a violent burst. Now they're operating at a whisper, but their residual influence could still be enough to drive the slower, steadier expansion we see today. It's like comparing a fireworks explosion to the slow burn of a candle. Both are releases of energy, just on vastly different scales. Some physicists take this further, proposing that dark energy isn't just leaking in, it's literally the pressure from adjacent dimensions pressing against ours. Think of our universe as a bubble floating in a higher dimensional foam. Other bubble universes might be pressing inward, while the energy of the higher dimensional space itself pushes outward. The balance between these forces could be what we measure as dark energy's elusive strength. This idea also offers a potential solution to why dark energy's density is so puzzlingly small. If it originates from higher dimensions, its effects in our universe would naturally be diluted, just as gravity appears weak because it spreads into extra dimensions. The math even hints that the observed value of dark energy matches predictions from certain string theory models where dimensions are compactified at tiny scales. Of course, the challenge is testing this. Unlike black holes or quantum particles, dark energy leaves no direct fingerprints. It's only detectable through its cosmic influence. But future experiments, like ultra-precise measurements of the universe's expansion rate or galaxy distributions, might reveal subtle patterns pointing to dimensional origins. Whether dark energy stems from hidden dimensions or something even stranger, one thing is clear. It's reshaping our understanding of reality itself. And if higher dimensions are indeed the source, that means the fate of the entire cosmos could be written in realms beyond our perception. So the next time you gaze at the night sky, remember, the empty space between stars isn't truly empty. It might be humming with the hidden energy of dimensions we've yet to uncover. Now let's take a closer look at a question that might seem simple but holds cosmic significance. What shape is our universe? At first glance, the answer might appear straightforward, but when we dig deeper, hidden dimensions could be warping the geometry of everything we know. Imagine the universe as a vast, expanding balloon. In this analogy, the surface of the balloon represents the three dimensions we experience: length, width, and height. From our limited perspective, this surface looks flat, just like the ground beneath your feet seems flat even though Earth is a sphere. But if you could step back and see the balloon from the outside, you'd notice its true curvature. The same might be true for our cosmos. Measurements suggest the universe is astonishingly flat on large scales. But this flatness could be an illusion, a side effect of extra dimensions folded in ways we can't directly observe. Here's where things get mind-bending. In string theory, some dimensions are theorized to be compactified, meaning they're curled up so tightly that even atoms are too big to detect them. Picture a garden hose stretched across a field. From a distance, it looks like a simple line, one-dimensional. But if you zoom in, you'd see the hose has thickness, a circular dimension wrapped around its length. In the same way, our seemingly flat universe might have tiny, hidden dimensions coiled up at every point in space. These extra dimensions could influence the overall shape of reality in ways we're only beginning to grasp. Now consider gravity's role in all this. Einstein taught us that mass warps spacetime, creating what we perceive as gravity. But if extra dimensions exist, they might add deeper layers of curvature, like folds in an invisible fabric. Some theories propose that the universe's flatness is a result of these higher dimensional folds balancing each other out. It's like a crumpled sheet of paper that, when viewed from the right angle, appears smooth. The true geometry could be far more intricate than we realize, with hidden dimensions subtly bending the rules of spacetime. What's fascinating is that this idea isn't just speculation, it has mathematical weight. Certain models of extra dimensions predict specific patterns in the cosmic microwave background. The the faint afterglow of the Big Bang. If scientists find anomalies in this ancient light, it could hint at the universe's hidden geometry. Even the way galaxies cluster or how dark energy behaves might carry fingerprints of these compactified dimensions. But here's the catch, proving it isn't easy. Detecting hidden dimensions would require observing phenomena at scales far smaller than atoms or finding subtle distortions in the fabric of space itself. Future telescopes and particle colliders might one day uncover these clues, but for now, the shape of the universe remains one of cosmology's great puzzles. So the next time you gaze at the stars, remember the night sky might not just be a flat canvas of light. It could be a living, breathing structure, its true form sculpted by dimensions beyond our sight. And if that's the case, reality is far stranger and far more beautiful than we ever imagined. Stepping beyond the visible fabric of space, let's explore one of quantum physics' most bizarre phenomena: particles that seemingly vanish and reappear as if by magic. This isn't science fiction, it's called quantum tunneling, and hidden dimensions might hold the key to unraveling this mystery. Picture an electron trapped behind an energy barrier, like a ball nestled in a valley between two hills. Classically, it shouldn't have enough energy to roll over the hill and escape. Yet, in the quantum realm, the electron occasionally pops up on the other side as though it teleported. How? One tantalizing theory suggests it might be taking a shortcut through higher dimensions. Think of it like an ant crawling on a folded piece of paper instead of trudging along the entire length. It could bridge two distant points by moving through the folded dimension. In the same way, particles might momentarily slip into hidden geometric folds, bypassing barriers in our 3D world. This idea gains traction when we examine virtual particles, fleeting entities that blink in and out of existence, borrowing energy from the vacuum of space. These particles aren't just random noise. Their behavior aligns with mathematical models where extra dimensions act as conduits. Imagine a game of whack-aim, all where the moles pop up not just on the board's surface but through unseen tunnels beneath. Hidden dimensions could provide those tunnels, allowing particles to tunnel through obstacles or even appear in two places at once. The implications are staggering. If particles can access higher dimensional pathways, it might explain why quantum systems behave so counterintuitively. Take superconductivity, where electrons pair up and glide through materials without resistance. Could their coordination rely on whispers through extra dimensions? Or consider radioactive decay, where particles escape atomic nuclei despite being locked in. Perhaps they're not breaking the rules, just bending them along unseen curves. Even more compelling is the link to black holes. Stephen Hawking showed that black holes emit radiation by spawning particle-antiparticle pairs near their event horizons, with one particle tunneling away. If hidden dimensions influence this process, it could redefine our understanding of black hole thermodynamics. Some theories suggest these dimensions might act like cosmic escape hatches, tweaking the rate at which black holes evaporate. Of course, proving this requires more than elegant math. Experiments with ultra-precise quantum sensors are hunting for anomalies in tunneling rates, deviations that might betray the presence of extra dimensions. Meanwhile, particle colliders could uncover higher dimensional fingerprints in the way virtual particles interact. So the next time you hear about particles defying classical physics, remember, they might not be breaking the rules, just playing by a higher dimensional playbook. Reality, it seems, has more layers than we ever dreamed. Now let's venture into one of the most mind-bending intersections of physics and philosophy, the idea that consciousness itself might be entangled with hidden dimensions. Imagine this: every time you observe a quantum particle, forcing it to choose a state, could your awareness be reaching into higher dimensions to make that happen? This concept stems from the infamous measurement problem in quantum mechanics. Before observation, particles exist in a blur of possibilities called a wave function, a superposition of all potential states. But the moment you measure them, this wave function collapses into a single outcome. Why? Traditional interpretations shrug and say it's random, but the von Neumann-Wigner interpretation dares to suggest consciousness plays an active role. And here's where hidden dimensions add a thrilling twist. What if the collapse isn't just happening in our familiar 3D space, but depends on interactions with other dimensions? Picture your mind as a higher dimensional entity. Part of your consciousness could extend into these unseen realms, influencing particles in ways our 3D brains can't fully grasp. Think of it like editing a document in a 2D window while the real processing happens in hidden layers of code. Your observation in our dimension might simply be the visible tip of a deeper, multidimensional process. Skeptics argue this sounds like mysticism, but mathematically, it's not so far-fetched. If particles can tunnel through extra dimensions, why not information or even the mechanism of observation itself? Some models propose that qualia, the raw feel of conscious experience, could arise from vibrations in Calabi-Yau spaces, those intricate 6D shapes we discussed earlier. In this view, your subjective awareness isn't confined to your skull but resonates across dimensions, subtly shaping reality at the quantum level. Consider the double-slit experiment, where particles behave as waves unless watched, then abruptly switch to particle-like behavior. If consciousness collapses the wave function, perhaps it's because observation links our 3D world to a higher dimensional scaffold where probabilities crystallize into certainty. It's as if the act of looking anchors the particle by connecting it to a more fundamental layer of reality. Of course, this isn't mainstream physics yet. Critics rightly point out that invoking consciousness risks straying into untestable speculation. But pioneers like Sir Roger Penrose have explored similar terrain, suggesting quantum processes in microtubules within brain cells might harness extra-dimensional physics. Whether these ideas hold up or not, they push us to ask profound questions. Could hidden dimensions be the missing link between mind and matter? And if so, what does that say about the nature of reality itself? For now, this remains a frontier where science, philosophy, and imagination collide. But as we develop tools to probe quantum gravity and dark matter, we might just find clues that consciousness and the dimensions it navigates are far stranger than we ever suspected. Now let's take a fascinating leap into the realm of biology and physics, where the very building blocks of life might whisper secrets about hidden dimensions. Could the complexity of DNA or the intricate wiring of our brains be shaped by forces beyond our three-dimensional world? The idea that life itself might be a product of higher dimensional physics is both thrilling and humbling. Think about the double helix structure of DNA for a moment. Its spiraling ladder isn't just elegant, it's mathematically precise, repeating patterns that seem almost too perfect to emerge from random chance. Some researchers speculate that this geometry could be a shadow of higher dimensional forms, a simplified projection of structures that exist in more complex dimensions. Imagine DNA as a three-dimensional printout of a higher dimensional blueprint, where the twists and turns encode information we can't yet decipher. Then there's the brain, neural networks, the web of connections that form our thoughts and consciousness mirror structures found in advanced physics models. The way neurons branch and interconnect resembles the fractal-like patterns seen in multi-dimensional mathematics. Could the brain be tapping into these hidden dimensions, using them to process information in ways we don't fully understand? It's a radical idea, but not without precedent. Some theories suggest that quantum processes in microtubules, tiny structures within neurons, might interact with extra dimensions, giving rise to the rich tapestry of human thought. Even evolution itself could have a dimensional twist. The staggering diversity of life on Earth might hint at influences beyond our observable universe. If higher dimensions subtly shape the laws of physics, they could also steer the development of life, nudging it toward ever greater complexity. Picture evolution not just as a random walk through genetic mutations, but as a journey guided by unseen dimensional landscapes. Of course, this is speculative, but that's where the most exciting science often begins. Could the emergence of intelligence require more than just time and chemistry? Could it demand the hidden architecture of extra dimensions? The answers might lie in future discoveries at the crossroads of biology, physics, and mathematics. As we push the boundaries of our understanding, one thing becomes clear: the universe is far more interconnected than we ever imagined. From the spirals of DNA to the firing of neurons, the fingerprints of higher dimensions might be all around us, waiting to be decoded. The next time you ponder the miracle of life, ask yourself, are we truly three-dimensional beings, or is there something more, something deeper, woven into the very fabric of existence? Now let's turn our gaze toward the horizon of discovery, where cutting-edge technology might finally reveal the ultimate fate of hidden dimensions. The answers we seek could lie in the next generation of scientific tools, from quantum gravity detectors to artificial intelligence-driven mathematics. These advancements may not only confirm or deny the existence of extra dimensions, but could also bring us closer to the holy grail of physics, a unified theory of everything. Imagine a device so precise it can measure the faintest ripples of gravity, distortions so subtle they've eluded detection until now. Quantum gravity detectors, still in their infancy, aim to do just that. By probing the fabric of spacetime at unimaginably small scales, these instruments could uncover signs of higher dimensions, perhaps catching gravity, leaking into them as some theories suggest. Even more intriguing, they might reveal microscopic black holes, fleeting evidence of extra dimensions predicted by string theory. While current particle colliders like the Large Hadron Collider haven't found definitive proof, future upgrades or entirely new machines could push the boundaries of what we can observe. Then there's the role of artificial intelligence. Modern physics deals with equations so complex they'd take lifetimes to solve by hand. But AI can sift through mountains of data, spotting patterns humans might miss. Machine learning algorithms could help decode the mathematical language of higher dimensions, testing predictions from string theory or M-theory against experimental data. Some researchers even speculate that AI might discover entirely new frameworks for understanding dimensions, rewriting the rules as we know them. What makes this search so electrifying is the possibility of unification. For decades, physicists have struggled to reconcile Einstein's general relativity with quantum mechanics, two pillars of science that refuse to fit together neatly. Hidden dimensions could be the missing piece, bridging these worlds into a single, elegant theory. Picture a cosmic puzzle where gravity, electromagnetism, and the nuclear forces finally click into place, revealing a deeper layer of reality. Of course, failure is also an option. Future experiments might find no trace of extra dimensions, forcing us to rethink our most cherished theories, but even that would be progress. Science thrives on disproving ideas as much as confirming them, narrowing the path toward truth. Whether hidden dimensions are confirmed or not, the quest itself is a testament to human curiosity. Every experiment, every equation brings us closer to understanding the universe's grand design. And if we do uncover these elusive dimensions, it won't just solve cosmic mysteries. It could revolutionize technology, philosophy, and our very sense of place in the cosmos. So while we don't yet have the final answers, the journey is far from over. With each breakthrough, whether through AI, quantum sensors, or sheer ingenuity, we inch toward a future where the universe's deepest secrets hidden in plain sight are finally revealed. And that's a future worth reaching for. As we wrap up this mind-bending journey through the universe's hidden dimensions, let's take a moment to revisit some of the wildest ideas we've explored. Remember those mysterious brains, the theoretical membranes floating in higher dimensional space that could host entire parallel universes? Or the holographic principle, suggesting our three-dimensional reality might just be a cosmic projection from a two-dimensional surface at the edge of the universe. And who could forget the eerie possibility that dark matter, the invisible glue holding galaxies together, might simply be matter from another dimension bleeding into ours through gravity? These aren't just sci-fi fantasies. They're serious scientific hypotheses that could solve some of the biggest puzzles in physics. Hidden dimensions might explain why gravity is so weak compared to other forces, why quantum particles behave so strangely, or even why the universe is expanding faster than expected. They could be the missing pieces in our quest for a grand unified theory, finally tying together relativity and quantum mechanics into one elegant framework. But let's be honest, this frontier is as uncertain as it is thrilling. We still don't have direct proof that extra dimensions exist. The math works, the theories are compelling, but nature hasn't yet handed us the smoking gun. Maybe future experiments will find it, or maybe we'll discover that the truth is even stranger than we've imagined. That's the beauty of science. Every answer leads to new questions, and the journey is just as exciting as the destination. So here's something to ponder long after this video ends. If there are dimensions beyond the ones we experience, what else might be lurking just out of sight? Could reality be far bigger, weirder, and more interconnected than we ever dreamed? The universe loves hiding its secrets in plain view. Maybe the next great discovery isn't in some distant galaxy. It's curled up in a dimension so small or so vast we haven't even learned how to look for it yet. If this kind of cosmic exploration sparks your curiosity, don't stop here. Hit that like button to let us know you want more mind-expanding content, and subscribe so you don't miss our deep dives into the universe's greatest mysteries. Tap the bell icon to get notified whenever we drop a new video, because trust us, you won't want to miss what's coming next. Until then, keep looking beyond the obvious. Who knows what dimensions you or science might uncover tomorrow?